We're looking at the related rates worksheet number 1 from 2.6. Conical water tank with a height of 40 feet and radius of 30 feet is leaking at a rate of 2 cubic feet per minute. When the height of the water in the tank is 30 feet tall or 30 feet deep, at what rate is the height of the water changing? So this is a problem that requires us to have to use similar triangles. Let's look at the figure first. We have the cone here, and we see that the water level is 40 feet deep. The radius is 30 feet, and we see the water level is somewhere between the bottom of the cone and the top of the cone. So from here, we can see the relationship in terms of the water level and the dimension of the cone using similar similar triangle, or a triangle within a right triangle within another right triangle. So we're gonna draw the figure here. This 30 represents the radius of the tank. 40 is the height of the tank. Little r is the radius of the water level, and little h is the height of the water level. Let's see what else we're given here. We're given that the water is leaking out of the tank at a rate of 2 cubic feet per minute. So you see the dimensions, or you see the units here. Cubic feet is representing volume per minute, so we know that has to be a rate dealing with volume. So we call that dV dt. Okay, so dV dt is dealing with 2. However, you see the word leaking, so that means this water is leaking out, which means that the volume of the water of the tank is decreasing. So because of that, we have to include dV dt as a negative 2 cubic feet per minute. Right? We know the height of the water in the tank is 30 feet, and we know we're looking for dH dt. We're trying to find out the rate at which the height of the water is changing. Height is h, rate of height is going to be dH dt. So now we're going to set up proportions using similar triangles. One thing that we're not going to touch yet is this h is equal to 30. This h equals 30 is the moment in time at for the height of this the water level. But we're not going to use this until after we found the derivative. So I think one of the most common mistakes I see with these problems, students want to plug that 30 in a little too soon. But you're not going to touch this until after you found the derivative. Okay, so we're going to leave that alone. We're going to set up proportions. The reason why we need to set up proportions is because we have too many variables in the equation and not enough information. So we have to find a way to replace one variable with another to simplify the number of or decrease the number of variables in the problem to allow us to find the derivative. So we're going to set up proportions here. So small radius is to the big radius, as small height is to the big height of the figure. So r over 30 equals h over 40. If we do cross product, we get 40r equals 30h. We're trying to get everything in terms of h, and the reason why is because we're trying to find dH dt. So dH dt was going to be a lot easier to come by if we have h in the equation, which will allow the derivative dH dt to show up. Okay, so 40r equals 30h. We're going to solve for r because we want to replace radius in terms of height. So r is equal to 30 over 40h, or 3/4 h. Now let's go back to our equation. The equation that we're working with is volume of a cone. So volume of a cone is 1/3 or pi over 3 r squared h. We're going to replace r in terms of h. So r gets replaced with 3h over 4. That's what we found here. So if we distribute the 2 through, the exponent through, we get 9h squared over 36 times pi over 3 out in front, and times the other h that we have. So another common mistake is students want to jump directly to find the derivative. But if we find the derivative here, we're going to have to go through product rule. It's a lot easier to try and clean this up and see if we can just resort to power rule. So we're multiplying the variables together. So h squared times h is h cubed. I'm going to combine all the coefficients together. So 9 divided by 3 is 3. So 3 over 16 pi. So now we have a lot simpler equation to work with than what we had here, but these are essentially the same, but we've simplified it so that the derivative procedure will be a lot clearer, a lot easier. So now we're ready to find the derivative. So the derivative for v is going to be dv dt. 3 pi over 16 is the coefficient, so it just stays out in front. We're going to find the derivative for h cubed, power rule, so 3h squared. And because we're just involved the derivative involving h, we have to attach dh dt. All right, so now we can work with this 30. We want to find out what is the height of the water level at this particular moment in time. So we'll plug 30 in for h. We can replace dv dt with -2, and then that leaves us with the only variable left, which is the one that we're looking for. We're trying to find the rate of the height of the water changing. So solve for dh dt. So now it's just a matter of multiplying by the reciprocal. So move the 9 pi 16 over, divide by 30 squared, and then we can use our calculator, or we can just try and simplify as much as we can to get dh dt. The rate of change of the height is a negative value. That makes sense. If water is leaking out from from the bottom of this water tank, then we expect the height to be decreasing over time. So -8 over 2025 pi, and the unit of measure is going to be feet per minute. All right, number 2. The volume of a cube is decreasing at a rate of 10 cubic meters per hour. How fast is the total surface area increasing when the surface area is 54 meters squared? So we're dealing with two equations here. We're dealing with volume of a cube, and we're dealing with the surface area of a cube. So volume is length times width times height, and we know all three dimensions for a cube will be the same. So we'll let x represent one of the lengths of one of the sides for the cube. So x times x times x will be x cubed. And because there are 6 faces of a cube, each area of each square will be x squared. And if we add up all 6x squared together, we're going to get 6x squared. So that'll be the surface area. We just basically add up all the areas of each of the 6 faces of the cube. All right, we're told that the volume of a cube is decreasing at a rate of 10 cubic meters per hour. So we know this is in reference to volume, cubic meters per hour. So we know it's dv dt. We see the word decreasing, so we know dv dt is going to be a negative value, so -10 cubic meters per hour. Okay. Let's just go ahead and also find the derivatives of each of these, since this will probably help. So v becomes dv dt, x cubed becomes 3x squared. We have to, because we're involving x's derivative, we have to attach dx dt. S becomes ds dt, 6x squared becomes 12x, and then we attach dx dt. When the surface area is 54 square meters, so surface area is 54 square meters, at that moment in time, we can find out what the length of each of the sides will be. So if we do 54 equals 6x squared, we know x equals 3. Now from here, we can use this information to help us find dx dt, and once we find dx dt, then we can use this to find ds dt. So it's a matter of looking at all the variables that we have and trying to piece together how we can find one piece of information at a time and plug in and get to our answer. All right, so we know x equals 3 will help us get to dx dt because we know what dv dt is. So dv dt is -10. X is going to be 3. And we're trying to solve for dx dt. So the rate of change of each length of the cube is going to be -10 divided by 27. It will be dx dt. And then once we have this information, then we can find the rate of change of the surface area, because we need x, which we found, 3, and we need dx dt, which we just found, -10 over 27. So 12 times 3 times -10 over 27 is -40 over 3. We're talking about surface area, so the unit of measure for surface area is going to be square meters, and then we're talking about the rate of change, so per hour. All right, number 3, we're dealing with similar triangle shadow problems. So these are very common. We're going to set up, I'll read the problem, and then we're going to set up the diagram. A light on the top of a 12-foot pole. So we have, for all these shadow problems here, we're going to draw a right triangle within another right triangle. So light on the top of a 12-foot pole. So here this represents the height of the large triangle will represent the pole. 5-foot tall person. So the height of the small triangle will represent the height of the person. Is walking away from the pole at a rate of 2 feet per second. So the distance between the pole and the person will represent x, and then the distance from the person to the tip of his shadow will represent that with y. All right, so now we can set up proportions here using similar triangles. So small height is to big height. So 5/12 is equal to the small base of the small base of the small triangle. Base of the small triangle is to the base of the large triangle. So base of the small triangle is going to be y divided by the base of the large triangle, which is x plus y. Common mistake here is students want to say 5/12 is equal to y over x. If we just do x, does not represent the full length of either of any base of any triangle. So we know x is not fit for setting up proportions here. So we have to represent that as the full base, so x plus y. Now, this is essentially the equation we're going to be working with, but I'm going to try and get it out of fraction form here. So we can cross multiply to cross product. So 5, distribute the 5 with the x plus y, we get 5x plus 5y equals 12y. Combine like terms, subtract the 5y over, we get 5x equal to 7y. Now we can find the derivative of each term with respect to time. So 5x becomes 5 dx dt, 7y becomes 7 dy dt. All right, let's see what else we're given here. At what rate is the tip of the shadow moving away from the pole when the person is 25 foot from the pole? So we were told that the person is 25 feet away from the pole. The person is walking away from the pole at a rate of 2 feet per second. So let me go over what each of these variables represent. So dx dt is the rate of change of the person walking either towards the pole or away from the pole. So that's the dx dt, rate of change of x. The dy dt, rate of change of y, when that distance is changing, that represents the rate of the change of the shadow length, the length of the shadow. Okay, and if we add the two rates together, the dx dt, the rate the person is walking, plus the rate at which the shadow length is increasing, then that will result in the speed or the rate of change of the tip of the shadow, how fast the tip of the shadow is moving. The tip of the shadow is moving based off of how fast the person is walking plus how fast the rate of change for the shadow length. So we're first trying to find the rate of the tip of the shadow. So the rate of the tip of the shadow is going to be, we're going to add the two rays together. But before we can add the two rays together, we need to first find out the rate of the shadow length. Okay, we know what dx dt is, which is rate of the person walking, which is 2 feet per second. But we need to know what dy dt is. So if we want to find dy dt, we're going to go back to this differential equation here. So dx dt gets replaced with 2, and we want to solve for dy dt. So 5 times 2 is equal to 7 times dy dt. Divide both sides by 7, and we get 10 over 7. So 10 over 7 is dy dt, so that actually is going to answer part B, the rate of change for the length of the shadow. So length of the shadow is going to be 10 over 7 feet per second, and so therefore the rate of change of the tip of the shadow, we're going to add the two rays together, the dx dt, which is 2, and the dy dt, which is 10 over 7. We add these together, 2 plus 10 over 7. It will be 24 over 7 feet per second.